Hello friends, today I am going to talk on modular arithmetic, sometimes called clock arithmetic. In mathematics, modular arithmetic is a system of arithmetic operation for integers other than usual ones for elementary arithmetic where numbers wrap around when reaching a certain value called modulus. The modern approach to modular arithmetic was developed by Carl Friedrich Gauss in his book Disquisitiones Arithmeticae published in 1801. Let us start with an example. A familiar example of a modular arithmetic is the hour hand of a 12-hour clock. If the hour hand points to 7 now, then 8 hours later it will point to 3. Ordinary addition would result 7 plus 8 equal to 15, but 15 reads as 3 on the clock face. We know that all the hour digits in the clock follow modulo 12. This is because the hour hand makes one rotation every 12 hours and the hour number starts over when the hour hand passes 12. We say that 15 is congruent to 3 modulo 12, written as 15 equal to 3 mod 12, so that 7 plus 8 equal to 3 mod 12. 7 plus 8 equal to 15, but 15 is 3 mod 12. If we divide 15 by 12, the remainder is 3. So that is modular arithmetic. Let us talk about congruence. Given an integer m greater than or equal to 1 called the modulus, two integers a and b are said to be congruent modulo m. If m is a divisor of the difference, that is, if there is an integer k such that a minus b equal to k star m, then we call a and b are congruent. Congruence modulo m is a congruence relation, meaning that it is an equivalence relation that is compatible with addition, subtraction, and multiplication. Congruent modulo m is denoted by a equal to b mod m. So when you divide a by m, the remainder is b. That is a equal to b mod m, or a minus b is divisible by m. Now let us look at some applications. Fermat's little theorem. If p is prime and does not divide a, then a to the power p minus 1 equal to 1 mod p. The proof is omitted, but this statement is proved first by Fermat, and this is known as Fermat's little theorem. Euler's theorem. If a and m are co-prime, then a to the power phi m equal to 1 mod m, where phi is the Euler tangent function. In number theory, Euler's tangent function counts the positive integers up to a given integer n that are relatively prime to n. Number of x that are relatively prime to n and less than or equal to n, that number is denoted by Euler's tangent function. And for Euler's tangent function, if a and m are co-prime, then a to the power phi m equal to 1 mod m. We have all got the proofs of it, but I am omitting them here. Wilson's theorem. If p is prime, if and only p minus 1 factorial equal to minus 1 mod m. So that's a characterization of the prime numbers, and this is known as Wilson's theorem. Chinese remainder theorem. For any a, b and co-prime mn, there exists a unique x mod mn such that x equal to a mod m and x equal to b mod n. That is known as Chinese remainder theorem. Lagrange's theorem. If p is prime and f x equal to a0 x to the power d plus a1 x to the power d minus 1 plus dot 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 plus a d x to the power 0 is a polynomial with integer coefficients such that p is not a divisor of a0, then congruence fx equal to 0 mod p has at most d congruent solutions. This is known as Lagrange's theorem. Primitive root modulo m. A number g is a primitive root modulo m if for every integer a co-prime to m there is an integer k such that g to the power k equal to a mod m. Then we call g is a primitive root modulo m. A primitive root modulo m exists even only if m is equal to 2, 4 p to the power k or 2 p to the power k, where p is an odd prime number and k is a positive integer. If a primitive root modulo m exists, then there are exactly phi of phi m such primitive roots where phi is the Euler-Taussian function. These are deep mathematics in number theory and all fall under the category of modular arithmetic. Quadratic residue. An integer a is quadratic residue modulo m if there exists an integer ax such that x square equal to a mod m. Euler's criteria asserts that if p is an odd prime and a is not a multiple of p, then a is a quadratic residue modulo p if and only if a to the power p minus 1 by 2 equal to 1 mod p. This is known as quadratic residue. Let us finish with a bit of talk on computational complexity. Since modular arithmetic has such a wide range of applications, it is important to know how hard it is to solve a system of congruences. A linear system of congruences can be solved in polynomial time with a form of Gaussian elimination. For details, see linear congruence theorem. Algorithms such as Montgomery reduction also exist to allow simple arithmetic operations such as multiplication and exponential modulo m to be performed efficiently on large numbers. Some operations, like finding a discrete logarithm or a quadratic congruence, appear to be as hard as integer factorization and thus are a starting point for cryptographic algorithms and encryption. These problems might be NP intermediate. Solving a system of nonlinear modular arithmetic equations is NP complex. All the talk is based on the Wikipedia article. I'll stop here. Like, comment, share, subscribe my video. I am available for one-to-one sessions also. Thank you.